right, so we are starting the material on statistical tests. This is also called hypothesis testing. And as I mentioned in the notes, the language, the notation, and the logic involved in statistical tests can be a little hard to get used to, right? So it's not as straightforward as we would hope. It seems kind of a roundabout way of running a test. But the good news is that even though we're going to learn several different statistical tests, the kind of framework and the language and the logic behind them will all be the same. So even though it will likely take some effort to get used to the language and the concepts involved, once you do, the payoff is that lots and lots of different statistical tests all look the same. It's just the sort of calculations and the mechanics that'll change, at least for the ones that we're going to do. So the first statistical test that we encounter is when we are testing a population proportion. So we're going to use one sample, so it's called a one sample test for population proportion. And we're going to kind of walk through the setup and then an example in this video. All right, so we always want to check hypotheses when we're running a statistical test to make sure that the test actually applies to the situation that we're in. For the one sample proportion test, these are the same requirements as for the central limit theorem to apply. So we need a simple random sample, so we're choosing members of the sample at random, and we have to have a large enough n that we expect at least 15 what we would call successes based on the probability of P naught, and 15 what we would call failures. So if the thing doesn't happen, that has probability 1 minus P naught, so n times that has to be at least 15. So we need at least 15 successes and failures, or expect to have at least 15 successes and failures in our sample. Okay, so the general setup is there's some population at large that we know something about, and then we're interested in some subpopulation, whether or not it's different in some way. So we might just be looking at a particular characteristic of a subpopulation, or we might be imposing some treatment on a group. But what we're really trying to figure out is, does that lead to some important difference between the subgroup we're interested in and the larger group that we might know something about? So the way we approach it is we start our statistical test by assuming that in fact there is no difference. And then we collect data to see if we have evidence against that assumption. Right? So instead of directly looking for evidence of a difference, instead we assume that there isn't any difference and see if we have strong enough evidence against that assumption. Right? So if we have strong enough evidence against the assumption of no difference, that is strong enough evidence that there is a difference. All right? So the assumption of no difference is called the null hypothesis. The null hypothesis should always look about the same. The notation is the capital H for hypothesis and the subscript 0 for nothing. You would pronounce this either H0 or H0 if you were reading it aloud. So the assumption of no difference is that the population proportion for our subgroup or subpopulation is the same as for the larger population that we know about. So we call P naught that proportion for the larger population, and we assume temporarily that our subpopulation has the same proportion as the larger one. Now what we're trying to figure out, we're trying to test to see if there's a difference in some way. Now, the way we think the difference should go is called the alternative hypothesis. So capital H for hypothesis, capital A subscript for alternative. And this can take one of three forms. Either we think our subpopulation has smaller proportion than the overall population, we might think it has a larger proportion, or we might think they're different and not really know which way it goes. So it's either a less than, a greater than, or a not equal to, and it's up to us to pick the one we want to use. So that depends on our suspicion or belief about the subpopulation. All right, so once we have our hypotheses written down, then we could go off and collect some data. We would take a simple random sample of size n. We would find the sample proportion in that data, and then we want to figure out how rare that sample proportion would be if there's really no difference between the subpopulation and the larger population. All right, well, this is why we have to make that kind of assumption, because in order to figure out the rarity of our sample proportion, that sample proportion has to have some distribution we can calculate with. So if we assume that there was no difference between our subpopulation and the larger population, then the central limit theorem applies, and we can assume that if that's the case, p hat is normally distributed with mean p naught and with standard error square root of p naught times 1 minus p naught all over n. Right? So that is the message of the central limit theorem, that in a simple random sample of size n that comes from a population with proportion p naught, the sample proportion p hat is normally distributed with mean p naught and standard error given as the denominator here. So it's the assumption of no difference that allows us to write down a distribution for p hat, which in turn allows us to figure out how rare p hat is. All right, so that's what's coming next when we calculate what's called the p-value. There are an awful lot of different uses for p on this board. We have capital P for p-value. We have little p hat, little p naught, little p, and then a capital P for probability, right? So it's a lot to keep track of. But the p-value, capital P, represents the probability of getting something at least as rare as the test statistic that we got. So if our alternative hypothesis was a less than, then we would want to know the probability of getting something at least as small as our z naught. So that's going to be a left-hand area. We want to figure out the probability of getting a z naught or something smaller. Or you can think of it in terms of p hat, the probability of getting that p hat or something smaller. All right, for the greater than alternative, we want the probability of getting a p hat or z-score at least as big as the one we did, so that would be everything to the right of z naught. And then the one that's a little confusing, I think, at first, if our alternative hypothesis was just not equal to, well, then we have to figure out the probability of getting something as extreme in both directions as the p hat or the z-score for p hat that we got. So that's a two-tailed area or two-sided area where we need the probability to the right of the positive value for z naught plus the probability to the left of the negative value for z naught. And because the normal distribution is symmetric, we can just take one of them and multiply by 2. Right? So that's where this 2 comes in. We're doubling one of these areas to account for the fact that we could have extremes in either direction if our alternative was just a not equal to. All right, so once we find the p-value, then we assess the strength of the evidence it provides against the null. And the smaller the p-value, the more evidence we have, or the stronger evidence we have against the null. Right? Because what that would say is that if the null were true, the probability of getting our p hat or something more extreme is really small. So it would almost never happen by chance if the null were true. So if something would almost never happen by chance if the null were true, then we doubt the null. So this brings us to the conclusion of the test, and we can do this conclusion in a couple of ways. But the final result is to either reject the null or fail to reject the null. Right? If the p-value is small enough, we're going to reject the null in favor of the alternative. But if the p-value isn't small enough, the language here matters. We don't accept that the null is true. We just fail to reject it for now. Right? So if we collect one simple random sample, and that sample does not provide strong evidence against the null, all we can say is we fail to reject it based on that sample. So if you ever find yourself tempted to write down accept the null, stop. Right? We don't ever accept the null. We just temporarily can't reject it. All right. So we're going to walk through this setup, which I know is kind of a lot of abstract notation, and try to put some particulars to it with the example 2 from the notes. And this is based on that survey that we did way at the beginning of the term, where one of the questions was about political affiliation for students. So in that survey, out of the 29 respondents, we had 14 students identify as Democrats, which gives us a sample proportion of 0.483 Democrats. And this P0 here is, I just did a quick Google search on the proportion of Democrats in Alabama currently. Right, so it's about 0.366. So what we want to do is test to see if there is a difference between political affiliation of BSc students and political affiliation in the state at large. So we've collected a sample, we found p hat, and we want to figure out if that provides strong evidence of a difference between BSc students and the state. Now, this one is maybe not it's a perfectly fine example to run through the calculations. This is not an example that we could include in a research paper because as we check the requirements for running the test, we actually failed them both. Right? We're going to pretend like that's okay for now and do the example anyway. But the first thing is this survey, remember, was not a simple random sample of BSc students. This was a convenient sample of the people that were taking my classes. Right? So it's not a simple random sample, so we have to be kind of skeptical about the results to start with. And then the second thing is we actually don't have a large enough sample, because if you multiply n, which is 29, times the population proportion 0.366, we only get 10.6, and that had to be at least 15. Okay, so we needed a bigger sample, and it needed to be random, but it still works as an illustrative example for us. All right, so let's set up the test. The null hypothesis is that our BSc students are no different in political affiliation. All right, so our null is that p is in fact 0.366. The alternative is the thing we suspect to be true. Now, for a variety of reasons, I think the expectation here should be that BSc students identify as Democrats at a higher proportion than in the state at large. So our alternative is going to be the proportion for our BSc students is bigger than 0.366, right? So that's the right-hand or right-tailed alternative hypothesis. All right, now we calculate the z-score or z-statistic for the p hat we got out of our sample. So again, what we're asking is how rare is that kind of result if there's really no difference? Well, it's 0.483 minus the assumed proportion over the square root 0.366 times 1 minus 0.366 divided by n, which is 29. Right, so all of that is under the square root. And I worked this out with my calculator a few minutes ago. The result is about 1.31. So that's our test statistic. And if you remember how to interpret the z-score here, this is saying that our sample proportion p hat is about 1.31 standard errors or standard deviation above the mean. Okay, now we want to figure out if that is rare enough for us to reject the assumption of no difference. Well, that calculation is based on the p-value, where we have to figure out the probability of getting a z-score at least as big as 1.31 because we had the greater than alternative hypothesis. Right, so somewhere on our standard normal, we've got 1.31, and we need to figure out the area to the right of 1.31. This is a problem for StatCrunch. And remember, StatCrunch gives you less area, so you have to do a subtraction for what you get. All right, so I went to StatCrunch and found the area to the left of 1.31. Subtract that from 1. That area was 0.905. And so our p-value is 0.095. Right, so our interpretation of the p-value is that if there was really no difference in a political affiliation between BSc students and the state of Alabama, the probability of getting a sample proportion of 0.483 or higher, that probability is 0.095. Right, so that's fairly low. It's not crazy low, but less than a 10% chance of getting a sample proportion like we got if there's really no difference. All right, now when it comes to concluding whether to reject or fail to reject the null, you can do it in a couple of ways. One is to just take the p-value and assess how strong that evidence is against the null, but typically, well, maybe I shouldn't say typically, but often there's a predetermined cutoff called the significance level that is your guide for whether or not to reject the null. So I don't think this is in the notes, but we are going to set alpha equal to 0.10. So alpha is the significance level. And setting it at 0.10 means that any p-value less than or equal to that value will cause us to reject the null. So the p-value here was 0.095. That's less than 0.10. And because it's less than 0.10, we are going to reject the null, that there's no difference, in favor of the alternative that BSc students are slightly more likely to be Democrats than in the state at large. Okay, so I think I didn't point out the alpha at the beginning. That's something that you do have to set before your study, right? So at least it was written up before we went through the example. But if there's a particular cutoff you want to use for your p-value, right, you have to set that before you collect the data. So it's not fair to look at your data and then go set the the alpha level for that sample. Okay, so there is at least one example for how to conduct a one sample proportion test. The Pearson homework has other opportunities, and there's one on the current worksheet as well. I expect there to be questions about this because it is kind of a lot and in some ways kind of weird the way the logic works. Hopefully you'll start getting used to it soon because this is basically the rest of the term. This idea of statistical testing, the mechanics might change for how we calculate our test statistics, but we're going to be stuck with p-values for the rest of the term and interpreting them. And in past classes that I've had, the p-value, more specifically the interpretation of the p-value, has been the hardest thing for students to learn if they haven't seen it before. So concentrate your efforts on making sure you understand the p-value and how to interpret it, because you'll be asked to do it a lot. Okay, that's going to do it for this video. I will do a quick video going through the StatCrunch calculations and also how to just run a test from start to finish in StatCrunch, which can be useful as well. Thank you.